Let us consider example 1, where we want to solve the following differential equation. We have 2 times the third derivative of y with respect to t, plus 5 times the second derivative of y with respect to t, plus 4 times the first derivative of y with respect to t, plus 3yt is equal to 6xt. Now to solve this, we want to put it into configuration form. That is, we solve for the highest derivative. The third derivative of y with respect to t would be equal to 3xt, our input into our system, less the quantity 2.5 times the second derivative of y with respect to t, plus 2 times the derivative of y with respect to t, plus 1.5 y of t. Now we can denote each of these terms a, b, c, and d, where a corresponds to 1.5 y of t, b corresponds to 2 dy dt, c corresponds to 2.5, the second derivative of y with respect to t, and d corresponds to 3xt. Now x of t is going to be our input, and y of t is going to be our output. Y prime of t is going to be the derivative of our output with respect to time, and so on. Now, in this form, it's very easy to see our input value, 3x of t, and what our multiplication factors are going to be, i.e. what particular op-amp we're going to have to use to scale our inputs. For instance, 3x of t will have to be multiplied by a value of 3, so we'd use a non-inverting operational amplifier with a gain of 3. Now, y of t must go through a non-inverting op-amp with a gain of 1.5, and then it could be followed by an inverting op-amp of a gain of -1. Or we could do an inverting op-amp with a gain of -1.5. There's various ways for us to achieve these gains. Now, if we put this in a block diagram, we can see what's happening. We have x of t, y of t, y prime of t, and y double prime of t. All 4 of these inputs will get multiplied by their respective gains and get summed to give us y triple prime of t. Now, that means we have to design an op-amp to give x of t our input, a gain of 3, y of t our first output, a gain of -1.5, y prime of t our output, a gain of -2, and y double prime of t a gain of -2.5. But there's a better way for us to do this. Now, a better way to do this is using an integrating and a summing operational amplifier system. First and foremost, we have x of t, our input into our system. We're going to run it through an operational amplifier with a gain of -3, and we will sum that to be part of our output. Now what we can do is take our desired output, y triple prime of t, and the negative thereof, and we can run this through a series of integrators with a gain of -unity. The first integrator we run it through with a gain of -unity will give us positive y prime of t. And we can run this through a non-inverting op-amp with a gain of 2.5 and sum that. Now if we integrate y double prime of t through negative inverting op-amp, this will give us -y prime of t. -y prime of t can get multiplied by a gain of -2 and be summed to a result. And lastly, -y prime of t can be integrated with a gain of -unity to give us y of t, which gets multiplied by a gain of 1.5. All this gets summed to give us -y triple prime of t. Through this process, the integration allows us to have a better signal than if we were trying to differentiate a particular signal within our system. Lastly, this can be visualized as follows. We have x of t as our input. We'll run x of t through an inverting op-amp with a gain of -unity. -x of t will go into our summing integrating op-amp, a combined op-amp, as opposed to use an individual summing and an individual integrating. This requires us to use one less op-amp within our system. Now the way the summing integrating op-amp works is we're going to have an output, y double prime of t. That was based upon the integration of y triple prime of t. Now we run this through an integrating op-amp with a gain of -unity, which gives us y prime of t. Y prime of t runs down and runs through an inverting op-amp with a gain of -unity, then gets added to our signal with a weight of 500 kiloohms. Y prime of t also runs through an integrating op-amp, again -unity, to give us y of t. And y of t runs through our system and get summed back to original signal with a weight of 667 kiloohms.